for line integrals on closed curves, what is a closed curve? A curve is considered closed if r of a equals to r of b. All right. Let me give you a pretty straightforward example. For instance, if you have the circle, the unit circle, to keep it simple, all right, whose parameterization is cosine t, sine t. Well, clearly this curve is closed, isn't it? It's closed because, it just goes around. But what if we start between, I start at 0 and finish at 2 pi? So that is a equals to 0, b equals to 2 pi. But do you guys agree this is the same point? It's just different value of t, but it's going to take us back to the same point. So that's what makes it closed. So evaluate this at 0 volt. You're going to get whatever value. I think it's going to be, so r of 0, that's going to be the vector 1, 0. Also r of 2 pi, that's also 1, 0, right? So we're getting the same for different points. So this satisfies the idea of r of a equals to r of b. That's what makes a closed curve. Okay, so here's the thing. If you evaluate, this is a very powerful theorem. If you're evaluating a line integral over a closed curve, given that the vector field is conservative, the value of the integral will be 0. Why is that? Because, again, so you're going from point A to point B along C1. Say this is, remember from last time the sideways parabola, all right? And then say this is the cubed one, right? So technically, what do we have? We have a closed curve there going in that direction and then back. So because that because that integral is independent of the path, well, whatever we get along C1, say 6, all right? And now, since it's independent of the path, it's going to be the same result as if we go by means of a diagonal line or a straight line. All right? But now, we want to go back along a different trajectory, but it's still going to be the exact same value of the integral. However, what happens? If this is 6, what's the value of the integral along C2? Notice it's going in the opposite direction. What will be the value? Negative 6. What is 6 minus 6? Or 6 plus negative 6? Alright, so that's what tells us that the value of the line integral over a closed circuit or over a closed curve is going to be 0. Alright? So, now here we have a summary of ideas, related to conservative vector fields, line integrals. So these three statements are equivalent here. Number one, so you will be given a force field, a vector field. Number one, check for conservative. If it is conservative, that means that any line integral you evaluate is going to be independent of the path. That means you won't have to evaluate anything, to parameterize anything. And number two, if you evaluate the line integral over a closed curve, it will always be 0. Notice the notation for line integrals over closed curves. It has like this little circle in the middle of the integral sign. All right, let's have a look at one example and wrap up the section. So we're given the force field given by f of x, y, z. This force field, so show that the integral along C of f dr is independent of the path and use the fundamental theorem of line integral to calculate the work done by f on an object moving along a curve. Again, it doesn't say which curve, right? So this vector field better be independent, better be conservative, because if it's not, then what would be the final answer? Not enough information is provided, right? So this better be a conservative vector field. Okay, let's check. Okay, let's check. So number one, let's check that m sub y, m with respect y equals n with respect x. That is m, n, and p. All right. So the derivative of m with respect y, that's cosine y, equals the derivative of n with respect to x. Alright, the derivative of x is 1 times the coefficient cosine, that's cosine y. The derivative of cosine z is 0 with respect to x. So first condition so far is satisfied. Number 2 is m with respect to z equals to p with respect to x. Alright, so m with respect to z, oh there's no z's, that's 0. That's easy. P with respect to x, oh no x's either, that's also 0. That's easy. Second condition satisfied. And number 3, n with respect to z, is that equal to p with respect to y? Okay, so n with respect to z, well, the first term is going to go to 0. Derivative of cosine, that's a negative sign. And p with respect to y, that's the derivative of negative y, which is negative 1 times sine z. That's a negative sign. Alright? So, the three conditions are satisfied. That means f is conservative, which means we can find the potential function. That potential function, it's a scalar function whose gradient is that force field. Alright, let's go for it. Let's do the partial integration. So m with respect x, that equals the integral of sine y dx, that is x sine y. X sine y, plus a constant that depends on y and z. The integral of n dy, okay, that's the integral of x cosine y plus cosine z dy. Okay, so that's the integral of cosine, that's sine, so that equals x sine y, and the derivative, the integral of cosine z, that'll be was that y cosine z, plus another constant of integration that depends on, what was that, x and z. Right, make some space for that. C of x z. Lastly, the integral of p with respect to z, that'll be the integral of negative y sine z dz. Careful, because the integral of sine is negative cosine. However, times that negative will become positive. So that's a plus. Y cosine z plus a function of x and y. Alright? Let's form our potential function. Let's highlight the different results. So number 1, x sine y with another x sine y. What else? What else do we have? Y cosine of z, y cosine of z. Alright? And again, to form our potential function, phi of x, y, z, in this case 3 variables, we only write one instance of it. We don't combine like terms. No, it's not adding together. It's putting this result together. Okay, so that is x sine y plus y cosine z. Final answer. And again, you guys and I know that there is a plus k, all right, involved on the behind the scenes. Okay, so that is the potential function. Let's evaluate the line integral using the fundamental theorem of line integrals, because again, the force field, the vector field is conservative. That means any line integral using this force field will be independent of the path. All right, and we will be able to use the fundamental theorem of line integrals. And also, well, even if you wanted to evaluate and use it using the method from 17.2, type 2 line integrals, well, there's no way, because they're just telling us a curve. They're not telling us which curve. You can make it up, that's fine, because it's independent of the path. But let's just use the fundamental theorem. That is the integral along c of f dotted with dr. That's phi of upper limit, that is 1 pi over 2 pi minus phi of 0, 0, 0. Okay, so this will be the function we just found, x sine y plus y cosine z from the origin 0, 0, 0 to the point 1 pi over 2 pi. Okay, upper limit minus lower limit, I mean this is just substitute, so that is x, which is 1 times cosine, oh no, sine y, which is pi over 2 plus y, which is pi over 2 cosine of pi, minus, you guys agree that if we substitute 0 for x and 0 for y, everything goes to 0? Okay, so minus 0. So this will be, what's that? 1 minus pi over 2. Alright? So that's the value of the line integral. That's the work done by the force. By the given force into moving a particle from the origin to the point 1 pi over 2 pi along any trajectory. Alright, and to wrap up this section, okay, part B. So this is what they're asking us to do. So evaluate the line integral for along a path that begins at the origin, passes through the point 1 pi over 2 pi, and then returns back to the origin. What do you think the result will be? Why 0? Because it's returning. What else besides it's returning? Okay, all right. That's good, and that's because regardless of the trajectory taken one way or in one on the way forward and then the way backward, doesn't matter if it's a different path, it's still going to be 0. That means, for instance, a picture A, which is 0, 0, 0, B 1 pi over 2 pi. So you can go from A to B along this trajectory, right? And then go back from B to A along this trajectory, right? So this is C1, C2. So the integral along C of f dr, this is the same as saying the integral along C1, I mean more formally, oh no, it's not a circle, plus the integral along C2 of f dr. And by this definition we had before, this is supposed to be 0, right? That's our 0. And this finishes the section.